So last time we finished up chapter 16 with the rate laws and all of that. So we are going to move forward into chapter 17. Now 17 is all about chemical equilibrium. Chapter 17 is also, if I remember correctly, the last chapter that's going to be on this upcoming test here in a couple weeks. Now, equilibrium. Equilibrium is an interesting concept. Now, basically, what we're talking about with equilibrium. Now, obviously, once you mix the different reactants and allow them to start reacting, concentrations are going to start changing. You're going to be losing the reactants and you're going to be gaining products. Obviously, products start at 0 and you're going to be getting more. But anyway, so right when you start the reaction, these concentrations are changing. But eventually, all of these concentrations are going to, well, equal out, and they're going to be remaining the same. So once you get to where the concentrations of your reactants and products are no longer changing, we call this equilibrium. Now, in the book on page 595, there's a graph that represents that. And it has to do with the production of ammonia from nitrogen and hydrogen. You can see the line for the hydrogen, and the line for the nitrogen, and the line for the ammonia. And all of these different concentrations are changing until they reach what we call equilibrium. And at that point, on the graph, we just have horizontal lines because the concentration is remaining constant, so it just levels out. Okay. Now, if the reactants, or at least one of the reactants, goes to 0 or, as close enough as it may as well be 0, we would say that reaction goes to completion. Okay, it does as much as it possibly can given the amount of reactants. Well, there's actually a lot of reactions that don't actually do that. If you notice in the graph, the concentrations of nitrogen and hydrogen don't go to 0. We still have some of our reactants left. And typically, the reason why we would have some of these reactants left is because these reactions are what we call reversible. And basically, reversible means you can reverse it. It can go the other direction. So the equation that we're starting with, we said, okay, we've got nitrogen and we have hydrogen. And we're making ammonia. And that's valid. We can do that. But the other thing that can happen, we can actually have ammonia break apart into nitrogen and hydrogen. So this is the exact same reaction, just written with the products and the reactants flipped. As long as the opposite way is a valid thing that can happen, this is a reversible reaction. Now, a lot of times what we will do, because we don't want to have to write out both things, we put a double arrow. So we see a double arrow, which tells us this reaction can go both directions. Sometimes this is how I will write the double arrow, just so you know. These two things are the same. Okay? It just kind of depends. If I know it's reversible, a lot of times I'll just go straight to this. But sometimes we write it one way and then like, oh yeah, that's reversible, so we throw that extra arrow on. Anyway, just so you know, those two things mean the same thing. So we have the forward reaction, which would be how we have it written, and then the reverse reaction, which is opposite. Okay. And the reason why a reversible reaction doesn't go to completion is because at some point, and we would call this equilibrium, at some point, every time we get one of these reactions over here going that way, we get one of these reactions going the other direction. Okay. And now that's an important concept. It's an important concept to understand that when we're at equilibrium, it does not mean that the reaction has stopped. It doesn't mean that the reaction has stopped. What it means is that the concentrations are remaining the same. So reactions continue to happen. It's just that for every time we go one direction, we come back the other way. So, you could think of it like, well, if you're in a boat, and all of a sudden, the boat starts to leak. Well, you get enough water in your boat, it's going to sink. You don't want that. So you start to, you grab a bucket, you start moving water out of the boat. Now, if the water is coming in at the same rate that you are dumping it out, the total amount of water in the boat is going to stay the same. Now, it's not the same water. You're getting new water coming in, but the total amount of water is the same. Okay, so that's what we're thinking of when we have chemical equilibrium. We have the same concentration of ammonia, but it's not the same ammonia molecules. Some of them will be forming and others will be breaking apart. But we have the same total number of ammonia molecules. Okay, so that's why we call it dynamic. So it's a dynamic equilibrium. Dynamic means motion. So we still do have a whole bunch of reaction happening. It's just, it's going in both directions and the concentrations are remaining the same. So, okay. The book actually spends a lot of time talking about that, just to make sure that, we really want to hammer home that idea that just because we're at equilibrium, it does not mean that the reaction has stopped. Okay? It is still happening. It's just concentrations that have stopped changing. Okay. Now, obviously, we like to be able to quantify things. We want to be able to say, all right, if we have this equation, this reaction that's going to happen, we want to know, are we going to get a lot of ammonia or just a little bit of ammonia? We want to be able to know that. So we had a couple chemists from Norway, actually, that developed the law of chemical equilibrium. Now, it allows us to generate what we call an equilibrium constant. Equilibrium constant. And the value of this constant is unique to the reaction and the conditions that it's under. But it's going to tell us, for this reaction under these conditions, how much product versus reactants we will have at equilibrium. So if we take just a generic reaction, so once again, the capital letters represent specific elements or compounds. And then the lowercase are the coefficients after you balance. Now, to write an equilibrium constant expression is what we call it. So once again, we're going to use K. Remember, K can mean all sorts of different things. We just have to figure it out based off of some clues. Now, the clue here is that we write EQ in the subscript, which means you're dealing with an equilibrium constant. And the way we do it, we take the concentration of the products. Now, this is important. We put the products on the top. And when we were talking about rate laws, we said you have to, determine the number that you put the exponent, the order of the rate experimentally. For this, it's actually nice. We just use whatever coefficient we have. So we put the products on the top and the reactants on the bottom. And that's really all you're doing with the equilibrium expressions. Okay. Now, if we look at this, so let's just think. If we have a whole lot more products than reactants, so most of our reactants are going to change into products. That means these concentrations are going to be large, and these concentrations are going to be small. So if you have a big number divided by a small number, that means your K, the value you get for K when you do the math, is going to be greater than 1. Okay? Anytime you have more over here than you have here, your K value is going to be greater than 1. Conversely, if you mix these together and it really doesn't produce a whole lot of that, you're going to have a small number up here divided by a bigger number. So if you have a smaller number divided by a bigger number, your equilibrium constant is going to be less than 1. So that's how we can judge these things. If your K value is large, it means lots and lots of product. You mix these things and they really just want to react. If your K value is low, that means you mix these things, and at least under the conditions that we've measured this, you're not getting very much. Okay. So, that's how we figure that out. Now, we'll get to a point where we put in concentrations and we'll work with actual equations to do this. But this is, just the concept, okay? So we're taking the concentrations of our products right here. We're going to use their coefficients, whatever we balanced it to be, right there. Then we're going to do the same thing for our reactants on the bottom. And then when we do have the actual values for the concentrations, we put them in, we do the math, we get a K value. Now, obviously, since this is a reversible reaction, we put that right there like that, we could write it like this. Okay. And obviously that's going to change our K value, because for this, we would flip it, right? Because these now are the products, and so they have to go on the top. So if you have a K value, it is specific to how you wrote the equation. If you write it in the reverse order, it's going to change your K value because it changes how this is written. So, now we do need to mention some stuff. There is a difference between what we call homogeneous equilibrium and heterogeneous equilibrium. Homogeneous equilibrium means all of your reactants are in the same physical state. Okay? They're all gas. They're all liquid. Okay? Means they're all in the same physical state. That is homogeneous equilibrium. And the nice thing about homogeneous equilibrium is that it follows that rule exactly. It follows exactly that example. We'll talk about heterogeneous and what you have to change for that. But anyway, let's look at this example problem, which is a homogeneous equilibrium. And it goes back to this equation that we had at the beginning. So we have our nitrogen, our hydrogen, and we're creating ammonia. So now the book does say, well, their steps, they write the general one. So they would say, okay, this is A, this is B, and this is C, which tells us that that equals C raised to the C, and A, B. So if following that pattern helps you figure it out, go for it. Now, I personally don't think it's that hard to go straight to the actual equilibrium. But maybe that's just because I've been doing it for years. Anyway, so if I were writing the equilibrium here, instead of doing that, I would just start looking at what we have. And write, okay, well, I know we're doing an equilibrium constant expression, so I'm going to write K sub EQ equals, and I'm going to start with my products. Okay. Now I only have one, So I write ammonia, the concentration of ammonia, and it's going to be squared because there's a 2 in the coefficient. And then I'm done with that. So here down on the denominator, I have the concentration of nitrogen. Now this one has an implied 1, so we'll leave an implied 1 right there. And then the concentration of hydrogen. We have to raise that to the 3rd power because there's a 3 right there. And that's our equilibrium expression. Pretty straightforward. Okay. If, like I said, if doing this pattern first helps you, go for it. Otherwise, you can go straight to just putting them in. Like I said, personally, that seems like just an extra step. But whatever. Do what is going to be easiest. So, okay. Now, heterogeneous equilibrium. That means that in your reaction, you have different physical states. You're going between solids and liquids, solids and gases, liquids and gases, you know, whatever it is you have, but they're not all in the same state. So the basic principles remain the same. Now you're going to use the same general formula. The only real difference is there are some things that we need to remove. If you have a pure liquid or a solid, they do not belong in your equilibrium expression. Okay. Now the reason for that is because concentration is tough when you're talking about liquids and solids. Okay. The reason is they don't change. Okay. The amount of moles per volume, you have a solid, it's not changing. Okay. Now you may have physically less of that solid, but that doesn't change the concentration of the solid. The concentration of the solid is dependent on the density. Okay, and that will tell you how many moles you would have in 1 liter. Okay. And the only thing that changes is how much of it you have, which is not what we're measuring. We're not measuring how much, we're measuring concentration. And since those are constants, we pull them out of the equation and we'll just say, okay, since our K value is a constant, we're just going to make it easy and put all of the constants together into one thing. So, when you are looking at these equilibrium expressions, okay, if anything at the, after, if it says S or L, we eliminate them from the equilibrium expression. Okay. And that's the only difference. So let's sort of set up an example of how that works. Okay. So here we have the baking soda. Okay. have our baking soda there, we can get, and let's remember to include our phases in this one because it actually does make a difference. Okay. So to write this equilibrium expression, once again, if you want to do the ABCD thing, go for it. Otherwise, say, okay, let's just start with our reactants. Now, if you write all of your reactants, oh, that's not balanced for some reason because I forgot that I made 2. Okay, now let's try it. So we have all of those, they're all 1s, so we don't need to put any exponents. And then we've got that. It's squared because there's 2. Okay. Now, if this were homogeneous, that's exactly what we would want. But this is solid, and this is solid. So that needs to be taken out, and that needs to be taken out. Once again, after you do these a few times and get some practice, you can skip this step. Right? Now, I've gotten to the point where I'm pretty comfortable in just putting what needs to be in there. But to start out, I would recommend that you start with putting everything just so you don't miss anything, and then eliminating, and then saying, okay, here's our answer. The equilibrium expression, the concentration of CO2 times the concentration of H2O. Okay, because that's what's left. That's what's left. Now, one thing that I will warn about, and this is something that I've seen happen. It's also very similar to something that I've warned about in doing math before. If we have something that looks like, well, actually, we can just look at the same reaction, but let's write it in the other way. So if we write add in the solids and the gases, it's important now. I think it is. Yeah. So if we look at that, if we write this equilibrium expression, K equals, once again, we'll just pull everything to start out with. Okay. Now, if we eliminate this and this, I have seen some people say, oh, we've only got 2 left. So we write it like that. That is not correct. We cannot take things from the denominator and move it to the numerator. What we actually have to do is 1 over that. So just be aware of that as you're doing your calculations and things like that. If you eliminate something on the top, you have to keep the 1. If you eliminate everything on the top, you've got to keep the 1. Obviously, if we eliminate everything on the bottom, I mean, you could write over 1, but that's sort of a waste of time because it just doesn't change anything. And that's why we tend to ignore it if it's on the bottom. So, but yeah, so once again, it another example of if you write it the other way, it's going to change the K value. It's going to change the K value. It's going to flip it. Because this is what we got the first time. Well, you flip it, and that's what you get. So. Once again, these K values have to be determined experimentally. Okay? We have to actually look at the reaction at equilibrium in order to determine what the K value is. Okay? And we can look up a bunch of K values. Okay? These are things that you could just plug into Google. What is the equilibrium constant of this reaction? And it will say, okay, under these conditions, the K value is this. Now, the book goes through some, and it gives example data, okay? And it shows how, if you start with specific concentrations, how it's going to finish. Now, if you look at that table, the finishing concentrations, all 3 of them are different. Okay? All 3 of those number concentrations are different. However, when you put it into the equilibrium expression, it all comes out with the same value, which means that they are all at equilibrium. You can have different actual numbers of concentration and have it be at equilibrium as long as the other ones have adjusted accordingly. Okay. If you're ever looking at equilibrium data, just because one is at equilibrium and the other one has different values for the numbers, the concentrations, it doesn't mean that the other one isn't at equilibrium. So hopefully that makes sense. Now this last example that we want to go over is, well, putting numbers in. That's the only extra thing that we're doing, okay? To actually get the value of K from experimental data. Now this example problem, they could have made it longer and, just giving you the equation again, or giving you a new equation, I should say, because what we're doing is we're building on the previous example problem, or maybe, it wasn't the one right in front of it, but example problem 1. So it says, they say, okay, well, we've already figured out the equilibrium constant expression for this nitrogen plus hydrogen gives us ammonia. Okay. So we know that our equilibrium expression is that. Okay, we already know that. And then it says, okay, so we've allowed this to come to equilibrium. And the concentration of our ammonia we measured at 0.933 moles per liter. Concentration of the nitrogen, 0.533 moles per liter. And the hydrogen has 1.600 moles per liter. Okay. Well, at this point, you take this, say, oh, concentration. So we're going to put this in here. Square it. Concentration. And okay. Then we just throw that in our calculator. And the hardest part of getting this answer is making sure you include all of your exponents and making sure you get your order of operations correct. Okay. Other than that, it's just putting it into the calculator and getting a number. Okay. Which this gives us the value of 0.399. Now, these equilibrium expressions, they don't really have units. Okay. It's just a numerical representation of where does that equilibrium lie. Do we have more products or do we have more reactants? Okay. So that would be our K value. All right. And since this is less than 1, it tells us that we have more of our products. We have more of our products than we do of our, sorry, I said that wrong. We have more of our reactants. We have more of our reactants than we do our products. Okay. Value of less than 1, you have more of your reactants than your products. So just to sum up what we talked about today, equilibrium. It means your concentrations have stopped changing. Okay? Once you start a reaction, the concentrations immediately start to change. Once they settle into what they are not changing anymore, you're at equilibrium. If it's a reversible reaction, then you're going to get back and forth, a dynamic equilibrium. And you're going to tend to have at least some of your reactants always present. You'll never get rid of all of them because you can always have some of your products go back. Now you can get really close, but if it's reversible, you're always going to have at least some. To write our expression to calculate, are we going to have more or less? Remember, we put the concentrations of our products on the top, concentrations of our reactants on the bottom. The exponent is whatever the balanced coefficient is. And then we can just put in the concentrations that we measure. So those will be given to you in order to get our K value. And that's it for section 1. As we move into section 2 and beyond, we'll talk about how we can shift this. If we have a low K value, we can talk about, well, what can we do to get more of the product? we want the product, how can we make that happen? So we'll talk about that and some other things as we go through the chapter. But that's where we'll stop for today. And as usual, we do have a homework assignment, so I'll put that on the board and start on that.